Swayam Prabha. Digital India. Educated India.
In the last class, actually, we were discussing about the distinction between spatial and temporal amplification theory used in linearized stability analysis. So, we came up to the spatial theory, where we said that the wave number components are complex in the x and z direction, that is the streamwise and the cross flow direction. And as a consequence of that, you notice that there is this path, which is essentially an amplitude, which is a function of y and x and z, and this is the phase path. And what we notice that because of this complex nature of this wave number components, we can define a direction along which the phase propagate, and that is given by this alpha r bar. Amplitude is given here and the direction is given by the tan inverse of beta r by alpha r. Then what we did was basically we defined the phase speed would be then given by the circular frequency divided by that amplitude of resultant vector, phase vector, the wave number vector. At the same time, having that imaginary part, we can define a sort of a alpha I bar indicating the magnitude of total amplification or attenuation suffered in a particular direction, that is given by psi bar, which is nothing but tan inverse of beta I by alpha I. So, that the compounded or the composite expression for the disturbance quantity as a function of space and time would be written like this. So, this is your amplitude A and this is your phase path. And then we did talk about that we have now two directions. One is x tilde, that is along that resultant phase direction alpha r bar, and x bar along the amplitude or decay direction, that is given by alpha I bar, and that is what you see in that equation 30 there. And as a consequence, you could find that quantity, the net amplification in that direction psi bar is once again given by this relative rate at which the amplitude changes. Okay. And what we note that if alpha is positive, then we have damped solution. If alpha is 0, then we have neutral solution, and if alpha is negative, then we have a case of spatial amplification. Now, what happens is basically that what we need to do is figure out how these two theories relate to each other. That comes about by considering the general dispersion relation, which tells you the circular frequency is a function of the wave numbers apart from any other parameters that you may have. And once you have the dispersion relation, you can calculate the group velocity given by this. It is implicitly understood that this wave numbers that appear in this expression alpha and beta, they are nothing but the real path, if it is if alpha and beta are complex, or if you are looking at the temporal theory, then alpha and beta are necessarily real, but then you will be taking omega as the real path of that is omega r. Now, I told you historically that people found solving the temporal problem easier for two dimensional problem, although there is not much of a difference between spatial and temporal theory, but suppose you are looking at a 3-dimensional flow, and then what you can do is you can get away from those complexities of defining that psi and psi bar. So, what you do is you perform a temporal theory calculation, having obtained the temporal rates etcetera, you can convert that into a spatial rate through a relation like this, and this relation was originally adopted by Schlichting in his 2D calculations. And as we see today that there is a basis for this equation 35, that comes out from the fact that this complex circular frequency are in general functions of the complex wave number components, right. So, what we could do is if we would do if we do write omega as omega r plus I omega I, and write one of the wave number in the x direction also as similarly like this. Then what we could do is basically we could write omega as a function of alpha, right. If I write this omega as a function of alpha, that immediately gives me this the following relationship between the partial derivatives of the real and imaginary part of omega with respect to this wave number component. How does it come about? That comes about because you say that this relation is analytic. What does it mean? That you have well defined derivatives everywhere, you can perform all that. And as a consequence of that, if this is an analytic function, you can actually get what is been taught to you earlier also, is that Cauchy-Riemann relation. Okay. And that Cauchy-Riemann relation is what is given here. Now, let us try to identify the meaning of the terms. Now, look at the first of the two Cauchy-Riemann relations. What is this quantity? The left hand side quantity that we have, del omega r by del alpha r. This is nothing but the x component of the group velocity. That is how we have defined, right. That is what you are seeing here also in the denominator. That is the Vgx, the group velocity component. And the right hand side, what we are noticing is a kind of a variation of the temporal growth rate with respect to the spatial growth rate. Now, if I draw this table here, that if I have a temporal theory vis-a-vis a spatial theory, then what are we getting? For a temporal theory, what we have? We have omega I, right, and what about the corresponding spatial growth rate, temporal theory, that is 0. So, that is that, and if I adopt instead a spatial theory, then what happens? Then I have alpha I and the corresponding alpha I and omega I should be equal to 0, right. So, if I look at it this way, then let me try to evaluate this partial derivative del omega I del alpha I. So, it is like suppose I am going from temporal to spatial theory, then this is my final condition, this is my initial condition, right. So, if I look at it and if I can try to write it approximately. So, what is omega final? Omega final is 0. What is omega I initial? Is the omega I itself, right? And then I have the final is alpha I initial is 0. So, what I get, this is nothing but omega I by alpha I. Well, of course, this is an approximation. Of course, this is an approximation for the derivative, but that is okay. This is okay. This we can live with it, because we are dealing with linear theory. So, the growth rates in space or in time are going to be small quantities. So, I can afford to take this kind of a first order approach in defining that. So, that is precisely what we do. Then what we do is basically write this quantity. So, del omega I by del alpha I is equal to this. So, that itself was Vgx. So, this is an expression for Vgx. So, Vgx simply turns out to be minus omega I by alpha I. What about Vgy? Vgy, you can do the same exercise. Now, instead of writing omega as a function of alpha, you write it as a function of beta, and once again the first of the CR relation, the Cauchy-Riemann relation would be given by this, and going by the same logic, this will give you the y component would be simply nothing but minus omega I by beta. Okay. That is what is written down in your transparency there. Okay. So, basically then you have the Vgx and Vgy component, right. So, the growth rate in the spatial theory gives you what? This, and that should be now what should we do? Dimensionally, if I multiply it by what should I get? That should be giving me the temporal rate, right. So, basically this is what one would like to do. If you have a 3-dimensional instability problem, you adopt a temporal theory, you work out the components, the temporal growth rate, so omega r, omega I, and then you try to estimate the group velocities through this type of approximation, and then convert it into the spatial growth rate, right. So, this is what it is. We will come back to 3-dimensional instability problems much later, but let us for the time being now talk about the nitty-gritty of solving a stability problem. We begin by the simplest possible case, which is also quite okay, as we discussed. The 2-dimensional problems are more relevant in many situations than 3D. So, let us look at 2D problem. 2D problem, the Ortsummerfeld equation that we have written down earlier. What was it? That was written in terms of the phi, and we had a 4th order ordinary differential equation. So, to solve that 4th order ODE, we require 4 boundary conditions, right. So, let us try to explore what those boundary conditions are and what those boundary conditions imply. Now, this is a given. This is given that at the wall, suppose I am talking about flow past a flat surface or a surface of mild curvature, then I can define my x axis along the surface. So, that would correspond to y equal to 0, and on that surface you have 0 disturbance velocity. Please do understand that we have some problem here, because I am emphasizing time and again that in nature you do not get something out of nothing. That means, you cannot have a homogeneous differential equation and homogeneous boundary condition and you get a non-trivial response. However, unfortunately, that is how all of you have been taught about this so called eigenvalue problem, that you take a homogeneous equation and you force a homogeneous boundary condition. That is what we are doing here. But I will show it to you what is the connection between a trivial and non-trivial boundary condition. Essentially, if I have a flow and that is unstable, and if I want to see its manifestation, I must have some kind of excitation. So, what I would show it to you very shortly, that I will provide some kind of excitation at the wall, and I will show that essentially those instability waves are getting created because of that. And I told you very clearly, you got to appreciate the fact that instability theory was propounded in the early part of the 20th century, but people had to verify it experimentally, and that took what, roughly about 40 years. And how did that come about? It is not by doing some arbitrary experiments. There the experiment was done in the following scenario, that you basically remove all possible trace of background disturbances, and then you excite the flow with a deterministic disturbance. So, basically, even though we write this, please pardon me for pointing it out time and again, that this is a very fancy way of doing mathematics part of it, but this does not add in understanding the physics of the problem. Okay. Nonetheless, if we are creating a disturbance inside the boundary layer, and if we go far away outside the boundary layer, then of course, we would demand those disturbance velocities would decay. That is what we have been doing. So, that relates to the Fourier Laplace amplitude of the u component and the v component going to 0 as y goes to infinity. Now, what is this 2.3.21? Let us hunt it back. So, we are basically writing down the Osmo field equation, which this phi 4 minus 2 alpha square we are writing it for 2 dimensional disturbance, right, and what we get is the other term is this. Okay. So, this is your Osmo field equation that we would just keep it here with us, and then we will talk about this. Okay. So, these are the 4 equations, but you see we need 4 conditions on phi, but we are given conditions on f. So, how do you translate that f condition into phi condition? That comes from a mass conservation, right. So, this is nothing but your del v del y term, and this is del u del x term, right. So, that is what we had obtained. So, basically if I give you a condition on f, that is equivalent to giving a condition on phi prime. So, essentially these 4 conditions that we have are given for phi and phi prime. That is the way we are going to use it. Now, we also see that in this equation the source of difficulty is that u and u double prime are going to be functions of height itself from the wall. And However, if I am looking at let us say flow over a flat surface with a sharp leading edge, a boundary layer forming like this, and if I go along this. So, basically you understand that orthogonal equation solution basically does the analysis on a particular station x and then solving this equation as a function of y. So, what happens is here you have this u of y. So, once you come to the edge of the shear layer, you have reached u equal to 1. Remember that we have non-dimensionalized all our velocities with respect to the free stream value. So, at the edge of the shear layer, that translates into 1, right. So, that is that. What about the second derivative? Second derivative is 0, because you are at the edge of the shear layer, all derivatives are going to be 0, and then this equation of course simplifies to this, right. I have omitted that alpha u double prime term, and wherever I had here alpha u. So, that becomes alpha minus omega. Now, why are you doing this? We are trying to perceive the property of the solution outside the shear layer. So, that is what it is, and in doing so, we note that as y goes to infinity, this becomes a constant coefficient ordinary differential equation, and that is amenable to analytic solution, right. A constant coefficient ODE, you can try out a trial solution of the following kind. You write phi equal to some e to the power lambda y and plug it back into this equation. So, you are going to get what? A quartic in lambda, right. So, you do that, and if you do that, you are going to get a quartic and then that would have 4 roots, characteristic roots, and what you find that equation that we had just now seen yields a pair of roots. 1 and 2 corresponds to minus alpha and plus alpha, and 3 and 4 corresponds to minus q and plus q. What is q? Q is this part. Remember that let me explain to you what is it that we are doing here. A little bit of explanation would not hurt. We are talking about y going to infinity. So, this equation is constant coefficient OD. So, let us write it down is equal to e to the power lambda y, and then from here I will get lambda 4, and there I will get 2 alpha square lambda square, and from here I will get alpha 4. So, that is the left hand side. On the right hand side, I have I r e, and u is 1. So, this becomes alpha minus omega, okay. And this will give me lambda square minus alpha square. This part goes away, right. This double prime is 0. So, what I get here is then I could take alpha out here. So, I could write here I alpha r e, and what I would get, this is 1 and this is omega by alpha. Omega by alpha is c. So, that is what we are going to get. Okay. So, you have a quartic now and you can solve it. So, what you are seeing that this is well, we can factor it out. We can factor it out. This is what? This is alpha square minus lambda square minus alpha square whole square, and that is equal to minus of I alpha r e into 1 minus c, and then I have lambda square minus alpha square. So, of course, this is equal to 0. So, you take lambda square minus alpha square common, and then I will get from here lambda square minus alpha square, and from here I will get this I alpha R e 1 minus c, well, put it in a square bracket, and this is what it is. So, you can see this factor lambda square minus alpha square gives you those lambda 1 2, and this quantity here alpha square plus I alpha R e, this we are writing it as something like q square. Okay. So, that is what we have written there. Q square is alpha square plus I alpha R e into 1 minus c. So, you can identify those 4 modes. There is of course, a very good reason to call this as the inviscid mode. Why we will call this as inviscid mode? Does not depend on viscous term, while lambda 3 4 are called the viscous mode, because the viscous action comes through that presence of R e term, right. So, that is what we identify. Now, so because you have a 4th order ODE as the governing Orson-Field equation. So, you would have 4 fundamental solutions, which we actually do not know how it is inside the boundary layer. It is only outside the boundary layer we know their behavior, that is what we have worked out, right. So, the asymptotic variation for y going to infinity is known, but we at least know it is a 4th order ODE. So, it should have 4 component solutions, right. Now, if you look at the behavior of this solution as you go up outside the shear layer, that means your y would tend to infinity, then what happens to the phi 2 part of the solution? Phi 2 part of the solution, phi 1 and phi 2 part of the solution for large y would be given in terms of this. This will go as e to the power minus alpha y, this will give you e to the power plus alpha y, right, and this will give you e to the power minus q y, and this will give you e to the power plus q y. Now, there is no reason on earth to expect that alpha is going to be only positive. Alpha is complex, but its real part can be positive as well as negative for the time being. For the ease of understanding, let us talk about the real part of alpha being positive. Okay. What happens if real part of alpha is negative? What do you expect to happen? Well, you can very clearly see that your phase speed is given by omega by alpha, if you are talking about 2 dimensions. So, if I get that as negative, that means what? The phase will go in the opposite direction. Okay? Well, similarly, one can talk about the group velocity, and one can truly find out if the disturbances are going downstream or upstream, right. So, we are alive to the situation, we are aware of the situation that we could have disturbances which go downstream, or we can have disturbances which can go upstream. At this point in time, let us focus our attention only to downstream propagating disturbance, and also the case where alpha r is positive. If that is so, then what happens to this part a 2 phi 2 as y goes to infinity is going to blow up, right. It is e to the power alpha y. So, y going to infinity, that will blow up. Same thing will happen if I do the square root and pick up both the parts, they are there. Then if I take the real part to be positive, then again for the same token a 4 phi 4 will blow up when you go to the edge and beyond the edge of the shear layer. Okay. That is what we are talking about here, that if we want to satisfy far field boundary condition, and if we consider the real part of alpha and q to be positive, then we must have this. So, that fixes those two constants A 2 and A 4 have to disappear. This is one of the thing. So, we are talking about a particular attribute of the disturbance field. What is this disturbance field going to be? That this is going like this e to the power minus alpha y and e to the power minus q y. So, the disturbance is predominant where? Closer to the wall, because as we increase the height we are going to decay. So, that is why the solution which will be composed of A 1 phi 1 and A 3 phi 3 will call that as the wall mode. You know the reason now why we call this wall mode, right. So, the disturbances may be created at the wall or near the wall, but they decay with y. That is why we are calling them as wall mode. Now, we can similarly also conceive of a situation where the shear layer is disturbed from outside. Why do we have to really think always the disturbances are created inside, and we need solutions which decay with y. I can have the completely the other situation, that I do not create any disturbance inside the shear layer, but the disturbances are going up. In fact, one of the very clearest manifestation of this is in the weather system. This rain pattern that we see in the whole belt starting from Iran all the way up to the northwest part of India, we get this winter rain. This is called the western disturbance. So, these disturbances are nothing but some kind of vertical disturbances which start off from the Caspian Sea region and go to the in the easterly direction, but from Indian perspective those disturbances come from the west. So, we call it as a western disturbance, but they actually travel in the east and they are outside the boundary layer. This massive vertical structures, those two get created, and as they migrate they create this rain. So, this is quite understood. In fact, I will show you some of the lab experiments we did about 10 years ago, where we did set up this so called free stream mode. A good example also comes from engineering side, when you look at what happens inside a gas turbine. There you would see, be it in the turbine or in the compressor. Talk about compressor, it is a cleaner flow, but you have the stacks of rotor and stator, rotor and stator. Okay. So, from the stator what do you get? You get vortices, right. Those vortices they go downstream, because that is the mean convection direction. When it comes over the stator, these vortices are not immediately ingested inside the boundary layer, but they remain outside the boundary layer, and those vortices originating from the stator, as they convect over the rotor, they create instability. That is a scenario what you would be calling as the free stream mode. Okay. So, there the disturbance resides in the free stream, and you want to find out what does it do inside. Okay. We will have a lot of discussion on this as we go along. Unfortunately, this is once again going to point out the drawback of mathematical physics stability theory. Stability theory does not distinguish between the two, right. There just you simply talk about homogeneous boundary condition at the wall and at the free stream. But if you do that, you miss this part, because here what you are saying, that as y goes to infinity, the disturbances do not decay, but they do attain a finite value, the one that you are prescribing, right. So, your disturbance should match up to that condition. It may be 0 at the wall. So, it will grow with height and it will saturate to the excitation level, but that is what is not very cleanly brought out by the stability theory at all. So, people have actually missed it. It was only in late 90s we have made this idea somewhat common to the knowledge of the research community. Let us now talk about wall modes and what properties we have. Let us look at the Orson field equation. Now, for the wall mode, we will have these two components as we discussed. We will have A1 phi 1 plus A3 phi 3. How do we evaluate these two multiplicative constants A1 and A3? That is what you want to do. Well, of course, it is a fourth order ODE. We have chosen the solution in such a way that the two conditions in the first stream have been automatically satisfied. So, what is left off for you to do is to satisfy the other two boundary conditions. They happen to be the wall boundary condition. At the wall, what we have? Phi and phi prime are 0. Stability issue, stability prescription. So, I will write that as A1 phi 1 as evaluated at y equal to 0, added to A3 phi 3 evaluated at y equal to 0, sum of these two has to be equal to 0. Same thing about this. So, now what happens is, this is where the mathematicians or the physicists they do say the correct thing, but they do it in an indirect manner. We have two equations for two unknowns. So, that we could write it like this. We will write it in this following manner that I have a coefficient A1, okay, and another coefficient is A3. So, let us write it this way. Let us write it in a matrix form that I have phi 1 evaluated at 0, that is what I indicate here, and I have phi 3 evaluated at 0, and my unknowns are basically A1 and A3. And the second equation tells me that phi 1 0 prime and phi 3 0 prime. And unfortunately, in stability theory, the right hand side is given as 0. Then we are trying to look for a non-trivial solution for A1 and A3. How can that happen? It can only happen if this matrix is singular, right. So, this matrix is singular. How can it happen? A determinant of that matrix equal to 0. And you see how they make life complex by just simply saying that this is equal to 0. So, that comes from if I call this as A matrix. So, we are going to say that determinant A equal to 0 corresponds to non-trivial solution. You understand what it is. Basically, if it is singular, then you get A1 A3 vector as 0 by 0 form, and by L'Hopital's rule you can get a non-trivial solution. 0 by 0, that does not mean 0, right. That is the whole idea of the stability theory, which remains somewhat obscured, right. So, that is what you are talking about here, that this will be non-zero when the determinant is 0, that will have this numerator by denominator both are 0. So, that means what? Physically we are saying stability relates to that condition that even when the numerator is vanishingly small, instead of 0, think of it as the vanishingly small quantity that is being divided by 0. So, division by 0 is what? Is a kind of a state of amplification. So, if the determinant go to 0 means what? You are amplifying the numerator. So, that is what instability means, that you have vanishingly small disturbance, but the property of the system is such that you are amplifying it. That is what it is. So, this is what is required of these two fundamental modes phi 1 and phi 3. evaluated at the wall should be equal to 0, and this will be equal to 0 for not all possible combinations of alpha and R e and omega, but only for selective configurations. Okay. I think now we realize clearly what we meant by stability theory as we have understood. Basically, that comes out that the fundamental solutions should be such that this combination would be equal to 0 at y equal to 0, and this will not be true for any arbitrary choice of alpha, omega and R e. This will only happen for a specific choice. So, if I fix R e, that means we are talking about a combination of omega and alpha that will help us satisfy this. So, there would be a combination of omega and alpha, and what is that we called? That is our dispersion relation. So, now you understand that for Orson field equation, the dispersion relation comes about for the wall mode by the satisfaction of this equation. This is what you need to do. Okay, so, this is understood, but phi 1 also satisfies the Orson field equation, phi 3 also satisfies, right. But each one of them, whether I am looking at phi 1 or phi 3, they themselves vary by different rates. Do we have any estimate for those rates at which it varies? Yes, we do. In fact, that is what we are seeing here. If we remove all of it, this is what we are seeing, that we have two quantities, right. So, phi 1 we know varies as e to the power minus alpha y, and phi 3 varies as e to the power minus q y. What did we also find? We have noted that q square is nothing but equal to alpha square plus I alpha R e into 1 minus c. So, if I look at modulus wise mod of alpha is complex, but still it can have it will have a amplitude that is significantly less than the mod q. Why? Because R e is a large quantity, we are adding to alpha square this. So, what does it mean? We have two component of solutions, they are decaying with y at a totally dissimilar rate, and whenever such a thing happens, we call that as the stiffness problem. So, this is related to and this is what we have talked about many a times, that this particular attribute of the solution makes it difficult to obtain it. I mentioned very clearly in the last class also that while Navier-Stokes equation was solved long before we could really solve this. This is essentially due to this, and this is a topic of mathematics called stiff differential equation. So, we have to worry about how to solve stiff differential equations. Okay. What does stiffness do? What does stiffness do? Stiffness does the following thing, that if you start off with a solution somewhere, let us say you start off from the free stream, because that is where you have the qualitative nature of the solution available to you. Now, you come down. As you come down, which one is growing more rapidly? This part, because now y is decreasing, right. As y decreases, this part will be overpowering that part. So, although you have two independent solutions, one seems to dominate over the other, and what happens is any background error, numerical error, tends to follow this, swamping the other component. So, you want two fundamental component of the solution to be alive at all points, because otherwise you will not be able to satisfy those wall boundary condition. In the process of integrating, if my solution is totally dominated by phi 3, I will never be able to solve this equation. So, that is your problem of stiffness. People have tried to do many things. We will not talk about many things, we will just talk about one thing in which we ourselves have participated, and that method which was developed to solve stiff differential equation is called a compound matrix method, which was originally introduced by two mathematicians, Ang and Reed. Also, there are other mathematicians like Professor Davies in UK. They have worked on it, but Ang and Reed wrote some very definitive nice paper available in Journal of Computational Physics. You can take a look at. This compound matrix method was developed basically to solve stiff differential equation. We have done some of this. I will tell you what this is. What we do actually, we see that phi 1 and phi 3 grows or decay at dissimilar rates. So, instead of working with the phi's, we work with a combination of phi 1 and phi 3, such that that particular variable set, all of the component varies with the same rate. So, that we do not have the stiffness. Okay. This is the basic philosophy, very simple. So, what we are really looking for, that we are looking for some combinations of the fundamental solutions of phi 1 and phi 3, and as a result we desire that these new variables should vary with y with an identical rate and help us remove the stiffness problem. Now, I have talked about in the context of solving this Gauss-Northfield equation, that it is a fourth order equation. So, if I say I have a solution, if I say I have a solution for phi 1, what am I talking about? What am I talking about? I know phi 1, I also know phi 1 prime. I think those of you who have been following how PDEs are classified, that is what we define the solution. So, this is one solution vector, and we have another solution vector, that is phi 3 prime, phi 3 double prime, and phi 4 triple prime. Okay. Now, what we try to do is try to generate a set of new variables, and what do we want to do? Because we have two fundamental solutions, so we try to form combinations of these two solutions in a 2 by 2 mode, right. So, for example, what I could do is I could take this, I could form one of the solution y 1, I could write it like this, phi 1, phi 3 and phi 1 prime, phi 3 prime. So, this becomes what? Phi 1, phi 3 prime minus phi 3, phi 1 prime. So, there you have it, phi 1 is this. Now, you can see that if you go outside the shear layer where phi 1 and phi 3 goes like this, what happens to this? Phi 1 times phi 3 prime, the exponential part, it will be e to the power minus within bracket alpha plus q. What about the second term? Also with the same thing. So, the growth rate has been like e to the power minus alpha plus q into y. Now, if I take this one and this one, then I will get y 2. You see, phi 1 phi 3 double prime minus phi 1 double prime phi 3. Now, once again I write this phi 1 and phi 3 like this and substitute it there. Then what do I find? The exponential part will still be same thing. So, at least we have ensured that y 1 and y 2 grow or decay at the same rate. So, what we could do is this 2 gave us y 2 and this 2 gave us y 1. So, if I take this one and this one, I will get, let us say, y 3, that is what we have. Then what we could do is we can see all possible combinations, and how many of those combinations would there be? 6. How do you get that? 4 C 2, right? That is what it is. So, you are going to get that. So, you see there would be this. So, what happened? Well, we are paying a bit of price because we started off with a 4th order ODE, and here we are introducing 6 variables. What about their governing equations? Well, the governing equations can be also worked out from the definition itself. See, y 1 was like this, right. If y 1 is phi 1 phi 3 prime, I will just show you a couple of them and then leave the rest to you. You can work it out. So, what happens is we defined y 1 as phi 1 phi 3 prime minus phi 1 prime phi 3. So, if I do differentiate it with respect to y, so that will be y 1 prime, and then we can see we will get phi 1 phi 3 double prime plus phi 1 prime phi 3 prime, and from here I could get a component phi 1 prime phi 3 prime minus phi 1 double prime phi 3. So, of course, you can see this cancels with this, and what is left with is y 2. So, that is what we have done. So, y 1 prime is y 2. You can do the same thing, y 2 prime, you will have these 2 components. You see, phi 1 phi 3 triple prime minus phi 1 triple prime phi 3 plus phi 1 prime phi 2 phi 3 double prime minus phi 1 double prime phi 3 prime. What is this? This is by definition y 3, and this is how we defined as y 4. Okay. So, we are generating equations for this compound matrix variable, they are also called the second compound. So, y 1 prime equal to y 2, y 2 prime equal to y 3 plus y 4. What happens to y 3? Well, y 3 as you can see, y 3 is nothing but phi 1 phi 3 triple prime minus phi 1 triple prime phi 3. So, if I do y 3 prime, I will get one part will be phi 1, phi 3 4 prime minus phi 1 prime, phi 3 prime, triple prime minus phi 1 triple prime, phi 3 prime, and then I will also have phi 1 4 prime, phi 3. Okay. This part is one of the compound, right, that we have defined. What about this part and that path? That is what we have identified. This part is that one of the compound variable. Okay. I do not know, I think it is y 5 or something. Yeah, take a look, it should be y 5. But what happens to this phi 3 fourth derivative and phi 1 fourth derivative? Because phi 1 and phi 3 are the solutions of Orson-Field equation, they themselves satisfy the Orson-Field equation. So, we could write it down, and I think that is what we will be doing in the next class. So, when we meet the next time, we will obtain all the solutions. Okay? We will stop here.